And we're back live again. I'm excited to take a look at some trigonometry questions with you. We're going to give people just a moment to log in as they're all notified that we are going live. This is going to be our, whoops, my computer just did a jump. That was my fault. Let me see if I can fix that. I don't know I can. Why is my computer weirding out? There we go. I got it fixed. We're ready. All right, we're back. Excellent. Well, I am excited to get started with you on this live. My computer's having a bad day. Okay, sorry about that. All right, so a big hello to everyone who's rolling in. Welcome to our live office hours for trigonometry, brought to you by Chegg. I'm at Wallace STEM. I'm excited to join you here today. You might recognize me from my channel at Wallace STEM on TikTok, Instagram, YouTube, and more. I do memes that are all about calculus or algebra, trigonometry, and I do trends. I say, come for the trends, stay for the math. It's a great page. Check it out if you haven't already. But for those of you that have been here before for one of our live events, I want to say welcome back. But there are some of you that are here for the first time, and I'm so excited to have you here. The goal here today is to help you understand your trigonometry class just a little bit better. You can think about this like your virtual office hour. I am here to help you in any way I can. So any questions you have, don't be shy. Stick them in the chat, and we're going to do our best to answer them throughout this hour. Well, to kick things off, I wanted to start with a little bit of a graphing problem because graphing sometimes is a big challenge in trigonometry. So I'm going to start with saying we're going to make a graph for the function y equals 3 sine of pi over 2x minus pi over 2, and then a plus 2 at the end. Now, before we graph this function, we first need to actually factor out what's in front of x so that we get an idea of what the horizontal shift is that's going to come from this. So first, I'm going to factor this pi over 2 out, which is going to make this function 3 sine of pi over 2 times x minus 1 plus 2. And then that puts this function in kind of the standard form of a function that we're used to seeing, where we have y equals something times either the sine or the cosine of some b times x minus the horizontal shift plus the vertical shift. And so it's important that we know and can recognize each one of these letters and what they mean. So first, let's start with A. A is the amplitude. So A, the amplitude, that's going to be my 3. We've got an amplitude of 3, which means this graph's going to rise 3 above the midline and 3 below the midline. The next number in here is B. B kind of helps us know what the period is. The period is always 2 pi divided by B. In this case, divided by pi over 2. Which, if we multiply by the reciprocal, that's 2 pi times 2 over pi, which allows the pi's to reduce out, giving me a period of 4. So that tells me that this graph is going to repeat every 4 units, which is also really nice because we can break a graph down into 4 parts. So I can see that every part is going to be 1 unit long. The next part we're going to be interested in is this h. That's going to be -1. That is our horizontal shift. And remember, we go the opposite direction you would expect. So we see a -1 here. That means we're going to move 1 to the right. And then finally, the last number here is going to be this +2 in the k position. That k position tells us the vertical shift. That tells me how the midline has moved on this graph. The vertical shift is 2 up. So with this information, we should be able to make a graph for this function. So let's give us an x-axis and a y-axis. 1, 2, 3, 4, 5, 6, 7, 8. We'll go 2 periods. And then we go 1 period backwards as well. I see the vertical shift is 2 up, and the amplitude is 3 above that. So this thing actually needs to come up as high as 5. 2, 3, 4, 5. We'll go up 6, and we'll do a couple down below. So when I see this vertical shift of 2 up, that's a good place to start. Go ahead and draw that midline in there. So 2 up, we've got a midline right here. It's not really part of the graph, but that's the point where the graph is going to cycle around. Next, I'm looking at this horizontal shift of 1 to the right. We have a sine curve. Sine normally starts right on the midline, but that's going to shift 1 to the right. I just went left. 1 to the right, which means the starting point for my graph is right here at 1. Then to get an idea of where I go from there, I might be interested in the amplitude. The amplitude is 3, so I'm going to go up 3, 1, 2, 3 from there. And I'm going to go down 3 from the midline, 1, 2, 3. And that tells me where the mins and the max are as this rotates through. The only thing left to really look at is the period. The period being 4. So if I go over 1, 2, 3, 4, I'm repeating the graph there. Go over 1, 2, 3, 4, repeat the graph there. Backwards 1, 2, 3, 4. The graph is going to repeat there. From the starting point, the graph is going to go up and it'll hit a maximum and then back to the midline halfway in between, which is a space of 2. And halfway between that, I can see I'm hitting the top, the bottom, the middle, the top, the middle, the bottom, and we kind of can get this connect the dot relationship going in this function here. And then we can draw our graph, and it's this beautiful sine curve that we were able to figure out from the original function. So that's a quick review of graphing trig functions, sinusoidal curves. There is a lot of great comments coming in though. One comment I see about the law of cosines. I see a couple comments about trig identities. So let's take a look at some of those things. Let's start with the law of cosines and then we'll dive into trig identities. You can never do enough trig identities. Wow, that doesn't want to erase. Hold on a second, I got backup for erasing. If all else fails, use the chemicals on the board. There we go. That's a little better. All right. So law of cosines, I think, was the question I saw, right? Yeah, from Ryan on Instagram. Wants to see some law of cosines. Law of cosines is really used in 2 different contexts. One context for the law of cosine is if I have a triangle, maybe 5, and maybe this side is 7, and the angle between them, let's say that's 28 degrees. We should be able to use that information to figure out the angle or the side all the way across from the triangle. The way we do that is we use the formula, and it's basically it's the Pythagorean theorem. You know the Pythagorean theorem is a squared plus b squared equals c squared. Now, the catch is what's different with the law of cosines is Pythagorean theorem only works if we have a right angle. If we don't have a right angle, we need some type of correction factor in there. And so that correction factor is subtracting 2ab times the cosine of the angle between them. So the angle between them, that's your angle C. A and B are the 2 other sides. Let's plug this stuff in. A is 5, so we have 5 squared, plus B is 7, we have 7 squared, minus 2 times A, which is 5, times B, which is 7, times the cosine of angle C, which we said was 28 degrees. That's going to equal C squared. What's nice about these types of problems is you can just plug them into the calculator exactly like it looks. So I can plug this in, making sure I'm in degree mode on my calculator because we have 28 degrees, not radians. So I can type in 5 squared plus 7 squared minus 2 times 5 times 7 times the cosine of 28, typing it all in your calculator in one foul swoop. And that should give me 12.19-ish. But remember, that's still equal to c squared. So to figure out what c is, we have to take the square root of that. And so c, the other side here, is 3.49. The other side is 3.49 units in size. So that's one way we can use the law of cosines, is if you know 2 sides and the angle between them, the law of cosines comes out quite nicely. Now, there's other times we can use the law of cosines as well. And that is usually when we know all three sides of a triangle. Let's say we've got 5, 7, let's see, that's 12. So, 5 and 7, that's pretty close to each other. Let's go 1, right? Yeah, that'd be a triangle. I want to make sure I don't accidentally make an impossible triangle, right? We can use the law of cosines to find an angle inside of this triangle. And usually with law of cosines, I like to go after the largest angle, just because that helps avoid the ambiguous case of the law of sines on as we find the other sides and angles. So the biggest angle is going to be across the biggest side. This is obviously not to scale. This is not 1 and that's 7, but not to scale. We're going to find this angle here. That's our angle C. So we're still plugging into the same formula. But remember, on either side of angle C, that's your A and your B. So when I use this formula, the law of cosines formula, we're going to do A squared, which is 5 squared, plus B squared. Whoops, that's not a triangle. Let me back up. Let me make this side 8. Because two sides, the two smaller sides have to be more than the other side. Yeah, okay. I digress. Sorry. I want to make sure that, yeah, thank you for catching that 2020 Abelard 12. I'm probably pronouncing your username wrong. Sorry about that. Yeah, you're right. That wasn't a triangle. I had the wrong side there. So let's make it 8. So we're going to have 8 squared minus 2 times A, which is 5, B, which is 8, cosine of C, and that's going to equal to the other side squared, C squared, which is 7 squared. Now, when I simplify this, we can't just type it in our calculator. The common error students do, and you don't want to make this mistake, is they type in all of this in their calculator to figure out what number goes in front of cosine. But remember, addition and subtraction is done separately from multiplication in order of operations. So I can do these, 5 squared plus 8 squared. That's 25 plus 64. What is that, 89? And then I can do these, minus 2 times 5 times 8, that's negative 80. Cosine of C equals 7 squared, which is 49. But I can't combine the 89 with the 80 because the 80 has a cosine on it. They're not like terms. We cannot combine things that are not like terms. So instead, we have to simplify this, solving it using our old solving methods where we subtract the 89 from both sides. And I get negative 80 cosine of C is equal to negative 40. I was not expecting it to come out so pretty. Did I do my math correctly? You're all checking my arithmetic, right? My mental math. Because when I divide both sides by negative 80, I get the cosine of C is equal to a positive 1/2. Yeah, that should work. And positive 1/2, you can do a cosine inverse of 1/2. And yeah, just like I was thinking, it's going to be a 60-degree angle. How nice is that? 60 degrees, exactly. Not bad for making up a problem on the spot. So that's the law of cosines. You can use it when you know 3 sides or when you know 2 sides and the included angle to help you solve the triangle. Excellent. Great questions coming in. Yeah, that's pi over 3 is the same thing as the 60-degree angle. Exactly right. I'm not sure why my computer doesn't want to scroll anymore. It's not being nice. See if I can scroll with my arrows. I can. We can scroll with my arrows. All right, so we're still good. There was other questions, though, about verifying trig identities, because what the HE double hockey stick was the comment. Yeah, let's talk about trig identities, because those are really going to be some of the more challenging problems. After we do some trig identities, we can come back and do some of those trig equations that you're asking about, WP on TikTok. We'll take a look at those. So again, this is your office hour. I'm answering your questions here on Cheg's live office hour. We are here weekly answering your questions. Make sure you take a moment to scan this QR code up in the corner, making sure that you're up to date on when we're doing all of our live office hours to answer your questions about trig, about calculus, about linear algebra, about economics, about chemistry, about organic chemistry. There are so many great live office hours. You don't want to miss out on any of them. Let's take a look at Let's try proving that cotangent squared of theta minus 1 over 2 cotangent of theta is equal to the cotangent of 2 theta. And this is a proof, not a solve. We're trying to prove this is true, prove this trig identity. When we're doing a trig identity proof, first thing I do is, if I have no idea where to go, no idea where to start, I'm going to change everything into sines and cosines. So cotangent is cosine squared, because it's squared, over sine, minus 1. Over 2 cotangent squared is cosine squared over sine. Oops, it's not squared, sorry. Sometimes the most challenging part of a problem is copying it correctly. So make sure you copy it correctly. All right. When you do this trick to change everything to sines and cosines, almost always you're going to end up with something in the denominator of these little fractions. So we need to clear out the denominators of those little fractions by multiplying by the common denominator, which in this case is going to be sine squared on top and bottom. And when we do that, it's going to have to distribute onto each term. So that sine squared reduces with sine squared, and I have cosine squared theta minus 1 times sine squared is sine squared over sine reduces with one of the sines, so I have 2 sine cosine. As you're doing these, we need to start getting familiar with kind of the format and the look of some of these trig identities, because you should recognize cosine squared minus sine squared is one of our important trig identities. It's one of the double angle identities. Cosine squared minus sine squared is the cosine of 2 theta. Also, you should recognize 2 sine cosine is one of our trig identities. 2 sine cosine, you might have to look it up on your cheat sheet of formulas, but 2 sine cosine, you should recognize that one is the sine of 2 theta, which means really I'm dividing cosine by sine. Cosine divided by sine is one of our trig identities as well. Cosine divided by sine is the one we used at the very beginning. It's the cotangent of these 2 thetas. And cotangent 2 theta, sure enough, that's what we were trying to prove. So we are done with our proof right there. Excellent question on finding those trig proofs. And we probably will want to do more of those, because those are probably the hardest challenge students have with their trigonometry class. But before we do another one, WP on TikTok was asking to do some trigonometry equations. So let's try doing some trig equations, and then we'll come back and talk about, but before I step away, there's a great point that was brought out by I don't know how to use Anmol Hazari. Cotangent squared minus 1, you're right, that is a trig identity. That's cosecant squared. So I could have simplified things a little bit as well by making that cosecant squared before I did the sine over cosine step, and that might have made things a little bit easier to simplify from there. So great idea there as well. All right, so let's do a trig equation, and then we'll talk a little bit more about what does it mean to take the sine, cosine, or tangent of an angle. Those are great questions that are coming in. Keep your questions coming in. This is your live office hour with Che. I'm so glad you're here joining us. We are going through trigonometry and answering all of your questions about your trigonometry course specifically. And a great question came up is, how do we solve equations using trig problems? So let's see if we can find a fun trig solving problem. Let's do cosine of 2 theta plus 5 cosine theta plus 3 equals 0. And if you want to see more proofs or more trig equations, practice more of those, go ahead and ask for that in the comments. Or if you have a specific problem that you want us to work on, stick that in the comment, and I'd be more than happy to try and work out your trig equation, your trig problem, your trig homework problem that you're looking at right now. All right, so Cosine of 2 theta hanging out with cosine of 1 theta. That's going to make solving a little difficult. Solving's a lot easier when everything kind of looks the same, either all cosines, all tangents, all something. What we do have is a property that can change cosine of 2 theta into cosines. Might need to look that one up, but cosine of 2 theta, there's actually 3 formulas for cosine of 2 theta. Cosine of 2 theta could be cosine squared theta minus sine squared. It could also be 2 cosine squared minus 1, and it can also be 1 minus 2 sine squared theta. We can use the basic Pythagorean identity to show all 3 of these are actually exactly the same. Here we have cosine hanging out in the rest of the equation, so I probably want the one that just has cosines. So let's make that substitution. Cosine of 2 theta is 2 cosine squared of theta minus 1. We've got plus 5 cosine of theta plus 3 equals 0. Let's combine like terms of the minus 1 and the plus 3. So we have 2 cosine squared theta plus 5 cosine theta plus 2 equals 0. And this gives us an equation that we can try and solve by factoring. Let's see if we can factor this expression. 2 cosine squared. How are we going to get 2 cosine squared? Well, 2 cosine squared is 2 cosines times a cosine. The last term times the last term has to equal the last term. So what times what equals 2? 2 times 1 equals 2. We can either go 2 times 1 or 1 times 2. One thing I like to think about is we don't want a factor to have a common factor in it. So if I put the 2 over here on the left, I'll have a 2 in both parts. We don't want to do that when we're factoring. So let's put the 1 on the left and the 2 on the right so there's no common factors. Let's see if that can give us 5. The outside gives us 4 cosines. The inside gives us 1 cosines. Sure enough, if everything's positive, that's going to give us 5 cosines. And then, once it's factored, we know each factor must equal 0. So if this factor equals 0, we can subtract 1 and divide by 2. And that tells us that the cosine of theta is equal to negative 1/2. With this other one, we can subtract 2, and that tells us that the cosine of theta is equal to negative 2. But there's a problem with that. If you remember, if you were here for the beginning of our discussion, you remember we did the graphs, and the graphs bounce up and down from negative 1 to 1. It's never going to actually equal negative 2. Well, unless you use complex numbers, but we're not doing that in this class. So cosine's never going to equal negative 2. We can just throw this one out right away. We're going to get no solutions from that, at least no real solutions. So then we just need to go to our unit circle and ask ourselves where on the unit circle is cosine equal to negative 1/2? Well, cosine is the x coordinate. So we'll go negative 1/2. That happens up here and down there. So now comes the task of, do you know your unit circle? Let's say we just want to give answers between 0 and 2 pi. If we go answers between 0 and 2 pi, this top one is going to be 2 pi over 3. This bottom one is going to be 4 pi over 3. Those are going to be our 2 solutions that when plugged in for theta, this expression is going to equal 0. 2 pi over 3 and 4 pi over 3. Excellent. Yep, that's the double angle identity. Exactly right. I've seen a couple requests for some trig substitution. That would be a great topic for our calculus broadcast. That's going to be tomorrow. So if you join us tomorrow, we can do some trig substitution. Make sure you scan this QR code over here so you know the schedule of when we are doing our various live office hours to help you out, answer your questions. A great question did come in. Domain of cosine is 0 to pi, I think. I think you're thinking the domain of cosine inverse. Cosine inverse is 0 to pi because if I know if I'm between 0 and pi, this is where we're looking for our cosine inverse functions. But cosine itself is actually defined for all real numbers, and the solutions we get are going to be between negative 1 and 1. To make it a function, though, for cosine inverse, it's not a function if we don't restrict the domain, and that's why we restrict it to 0 to 2 pi. All right, a great question came in about what does it mean to take the sine or the cosine or the tangent of an angle? To answer that, we need to go back to our unit circle. Back to our unit circle. In your trig class, you get really good at drawing unit circles. Should I enter a contest for making perfect circles? There's actually a contest for that. I would do terrible. My circles are always lopsided, as you can see. All right, so the idea is if I pick some angle on this unit circle, let's pick an angle. Let's go 7 pi over 6. So we got this angle over there. We want the sine of 7 pi over 6. Sine is another fancy way of saying, I just want to know what the y coordinate is on an angle of 7 pi over 6. What is the y coordinate here? The y coordinate is this little distance right here, which is going to be 1/2 down. So the sine is -1/2. The cosine of that angle, what does it mean to take the cosine of that angle? Cosine means I want to know what the x coordinate is. I want to know what this distance is over here. I'm going to move my label 7 pi over 6 outside of the circle because we're going to do something in here. 7 pi over 6, that distance here turns out to be the square root of 3 over 2. So the cosine, it's backwards because we went to the left, is negative square root of 3 over 2. That's what it means to take the sine and the cosine, because ultimately what we're doing is we're looking at this triangle where we've got the angle theta here. Sine, we know sine as the opposite over the hypotenuse. Well, the hypotenuse of this triangle is 1 because it's the radius on the unit circle. And yes, great question. We'll do secant, cosecant, and cotangent too. So opposite would be -1/2 divided by 1 gives us -1/2. That's what we're doing when we find the sine and the cosine. Now the tangent is the opposite over the adjacent. Tangent is the y divided by x. Tangent is the sine divided by the cosine. It's all the same thing. In fact, you can even think of tangent as the slope of the radius on the circle, which is kind of cool because it's really doing the rise over the run. It's the slope. So in this case, we're going to do -1/2 divided by -1/3, the sine divided by the cosine. What's nice is almost all of your points have 2 in the denominators. So for tangent, the 2 in the denominator reaches out, and I just have -1 over -3, which is +1 over the square root of 3. And if you want to rationalize that, you can. I'll do that in a different color just to emphasize it's different. Rationalize that by multiplying by √3 on top and bottom, so we get √3 over 3. That's the tangent of the point. Now, a follow-up question came in. What about the cotangent, the cosecant, and the secant? Those are just the reciprocals of these 3 fractions. And so we can also do, let's do the cotangent here. Cotangent is the reciprocal of the tangent. Cotangent is 1 over tangent. So in this case, we could flip this over to get the square root of 3 over 1. Another way to think about the cotangent is the cosine divided by the sine. So we could take the negative square root of 3 divided by -1, or you could think about it as the x divided by the y. All of those are the same thing. What about the secant? You got to remember, who is the secant the reciprocal of? Secant is the reciprocal of the cosine. Remember, you never have 2 cos or non-cos together. So cosine goes with secant, cosecant goes with sine, cotangent goes with tangent. Secant is the reciprocal of cosine, so we're going to take this -2 over √3 over 2 and flip it over to get -2 over the square root of 3. And again, you can rationalize that denominator. Some teachers are more picky about this than others. I'm not picky about it, but I know a lot of teachers really want you to rationalize your denominator. So multiply by that square root to get -2 √3 over 3. And then finally, the last one is the cosecant. Cosecant is the reciprocal of the sine. So this -1/2, flip it over, and we get -2. And those are the 6 trig ratios. Now, one thing to be careful of with the trig ratios is making sure that you get your signs right. So let's take a look at a nice little trick about the signs that I like to remember. When I'm trying to think about my signs for sine, cosine, and tangent, by sine I mean positive, negative. I don't mean sine, cosine, sine. To help me remember what things are positive, I think about the phrase, all students take calculus. If you can remember all students take calculus, starting with quadrant 1, all students take calculus, that tells you who is positive in that quadrant. So up here, all sine, cosine, and tangent, all of them are positive right here. S stands for sine. Sine is positive here, which means the other ones, cosine is negative, tangent's negative. Down here, tangent is positive. Tangent is positive, which means the other ones, cosine and sine, are negative. And sure enough, cosine and sine were negative, tangent was positive. Over here, we've got C stands for cosine. Cosine is positive over here. And so if the angle's in this quadrant, cosine's positive and the sine and the tangent are negative. So if you can remember all students take calculus, you can remember what's positive and what's negative. Excellent. I saw a comment about polar images of complex numbers. That's a really fun topic. So let's take a moment to dive into polar coordinates for complex numbers, because it's pretty amazing what we can do with a complex number. Let's say I've got a complex number that is like 2 minus the 2 square root of 3 times I. And I wanted to figure out what this is to the 10th power. That would take forever, because I have to multiply this by itself 10 times. It probably wouldn't even fit on my whiteboard. There's just not enough space for it. But we can change this complex number into its polar image using a real nice trick. We're going to call this real part, the 2. I'm going to call that A. The coefficient of the imaginary term, I'm going to call that B. We're going to change this to a polar complex number where the radius squared is equal to A squared plus B squared. Well, if the radius squared is A squared plus B squared, the radius squared is 2 squared plus -2 root 3 squared. Well, 2 squared is 4. 2 squared is 4 times square root of 3 squared is 3. 4 times 3 is 12. 12 plus 4 is 16. So the radius here is equal to 4. Then what I need to do is figure out the angle that's going to correspond with this complex number. Great question. What is I? Sorry, I skipped over that. I is the square root of -1. A lot of the times we need to do the square root of -1 in order to solve different applications, especially in physics, electrical engineering, and the like. And polar form is going to give us a way to handle that a lot easier, because we change to what we're really doing. Maybe I could even back up a little bit. What we're really doing is we're graphing the real part on the x-axis and the complex part on the y-axis. So I'm saying we're going to go over 2 and down 2 root 3. And that point is going to be represented not in rectangular form, but in polar form. And we're going to figure out what is the radius to that point and what is the angle that gives me that point. So we've got the radius. The way we get the angle is we're going to divide the A by the radius, and we'll divide by the B by the radius. And when I reduce that, it's going to give me a coordinate point of 1/2, -root 3 over 2. That should look like a familiar point from our unit circle. Sure enough, on the unit circle, if I go x of 1/2 and a y of -root 3 over 2, that's going to be, what is that, 5 pi over 3? that is my angle. So we're going to represent this complex number of 2 minus 2 root 3 times the square root of negative 1, I. That complex number can be rewritten as the radius times the cosine of my angle plus I times the sine of my angle. And if you don't believe this, you can just evaluate the cosine of 5 pi over 3. That's 1/2. 1/2 times 4 is 2. You can do the sine of 5 pi over 3. That's negative root 3 over 2. Times the radius of 4, that's negative 2 root 3. So it's exactly the same thing. I just lost my chat. I don't know what happened there. I got an error that something went wrong. I lost my chat. So hopefully I'm still live and you can still hear me. We're going to keep going. I assume we're still broadcasting. I think my chat just glitched. What's nice about this polar form is it's going to make doing a 10th power a lot easier. So I'm going to say we want to take all of this to the 10th power, because how this works. All right, how this works is, well, it's part of it's going to get really big. We've got 4. The radius gets raised to the 10th power. And I'm not going to evaluate that. That's a huge number, but we'll just leave it as 4 to the 10th. It's 1,024 squared. Anyways, we're not going to do it by hand. Then each of these angles is actually going to get multiplied by that exponent. And so we have the cosine of 5 times 10 is 50 pi over 3 plus I sine times 50 pi over 3. And now we have taken this complex number to the 10th power without having to multiply it out 10 times. And so that can save us a lot of work. Polar form of complex numbers. There are formulas we can use to multiply complex numbers, divide complex numbers. We can do exponents. We can do roots of complex numbers. Lots of great things using them as polar form, which is really, really nice. All right, I got another request to verify trig functions. I assume you mean verify trig identities. So let's do some more of those. Remember, this is your office hour to review your trigonometry class, answer your questions, tell me what you're working on in your class, and we will continue answering those questions during this time. So keep sticking them in the chat. Let me know. We need to do some more proofs, though, I think. Here's a proof that I don't think is as intuitively obvious, so it's kind of a fun one. Let's look at cosine squared of theta plus cotangent of theta divided by cosine squared of theta minus cotangent. Excuse me. We're back. Sorry about that. Minus the cotangent of theta. We're going to show that's equal to the cosine squared of theta times the tangent of theta plus 1 over the cosine squared of theta times the tangent of theta minus 1. Now, the thing with proofs is we have to manipulate one side, work on one side to make it look like the other side. So how do we do that? Well, we pick the side that looks the most complicated. Which one's most complicated? If you're not sure, just pick one. Try it out. Let's see what happens. I see a little bit more happening on the right side. So let's play with the right side this time. Excellent. We've got the shout out to Mandy. Hello. Welcome, welcome. Glad to have you here. This is your Trig Office Hour brought to you by Che. Excited to have you here. We are manipulating this right side to try and make it look like the left side because this is a proof problem. So again, first thing I'm going to do is change everything to sines and cosines because tangent is sine over cosine. So I'm going to say cosine squared of theta times tangent, which is sine theta over cosine theta plus 1 over cosine squared times tangent, which is sine theta over cosine theta minus 1. This is really nice because normally we have to multiply to get things out of that denominator, but this one actually comes out really nice so that the cosine in the denominator reduces with one of the cosines in the numerator. And the cosine in the denominator is going to reduce with one of the cosines in the numerator. So now I have cosine theta sine theta plus 1 over cosine theta sine theta minus 1. All right, now here's where this one gets tricky. Let's see if we can be clever and come up with what we really need to do to fix this. We want to have a cosine squared. We have a cosine. We don't want to have the sines. So I could get cosine squared by multiplying by another cosine of theta. That would give me cosine squared. So I would multiply that on top and bottom, and then distribute it through cosine, cosine, because now that's going to give me cosine squared. Cosine squared, that's what I want. I don't want these signs here. How do I get rid of these signs? Well, what if we just divide them out? Whoops. What if I divided by a sine? Divide by a sine. Divide by a sine. Divide by a sine. Notice by doing that, the sine reduces out with the sine, and it gets rid of the sign that I don't want. Also here, the sine reduces out with the sine, and it gets rid of the sign that I don't want. But what's even better, look what we created on the right side. Cosine over sine, that is the cotangent. And what do we want on the right side? We want the cotangent. We actually accidentally built exactly what we were looking for. So cosine times cosine is cosine squared, plus cosine over sine, that's cotangent. Over cosine times cosine is cosine squared, minus cosine over sine, that's cotangent, which is exactly what we're trying to prove, what we're trying to get on the other side. So that is done, QED. I saw a great comment come in though. Could we not have just multiplied by tangent, cotangent? What did you say? Multiply by tangent over tangent. Yeah, that would have worked too, actually. That would have been even quicker. Good observations. Let's do that because first off, with proofs, there's not always one way to get there. There's lots of ways to get there. So don't get bogged down in doing the right one way. Just start trying things that you see that might work. And somebody put in the comments, who was that? That was Math Nerd. Hey, Math Nerd. I know you. We follow each other, I think. Good observation is to notice, hey, what's different about these? This one, the cosine squared, is missing the tangent. So just multiply a tangent in on top and bottom. And when I do that, that tangent's going to distribute through and multiply by the other side. Well, now I've got cosine squared tangent plus cotangent times tangent. Remember we discussed about cotangent and tangent? They're reciprocals of each other, which means one will reduce out the other. So cotangent times tangent is just going to be equal to 1. Because cotangent is 1 over tangent times a tangent. You see those reduce out, leaving just the 1. All over, then we have a cosine squared theta times tangent theta minus, again, cotangent times tangent is 1. And that gets me in one step right to the solution, which is really nice. So good work there on seeing that. Excellent question. All right, Let's move on to another topic. Remember, this is your office hour brought to you by Chegg. We are looking specifically in this hour at trigonometry. So what trig questions do you have? Are you doing polar? Are you doing proofs? Are you doing the unit circle? Do you want tips to memorize the unit circle? Do we want to do more proofs? Do we want to do more solving? What do you want to see? This is your office hour. What are you working on in your trigonometry class? Stick it in the chat and we will take a look at it. Chris just wants to do another problem. I assume you mean another proof. You can never seem to do enough practice with proofs. So we'll go ahead and do another proof. And then you can go ahead and stick in the chat any other questions that you have. Let's see if I can find a more exciting proof. Let's try. Let's try sine minus cosine. And then we'll divide it by secant minus cosecant. We're going to show that's equal to the sine times the cosine. Excellent. Seeing more proofs, more sine problems. Well, that's what we're going to take a look at right here. Again, with a proof, if you are not sure what direction to go with the problem, I would suggest you start by just changing everything into sines and cosines. So let's do that. We've already got sine minus cosine. Secant is 1 over the, who's it the reciprocal of? It's the reciprocal of cosine. Minus cosecant. Who's cosecant the reciprocal of? Sine. When you do that step, almost every time you're going to end up with little fractions inside of a bigger fraction. And so quite often the next step to go to from there is to get rid of these little fractions by multiplying numerator and denominator by that common denominator. So we've got a cosine and a sine in denominators. We're going to multiply it on top and bottom. When we do that, it's going to distribute onto both terms. To make it easier, I like to write it on both terms. Cosine, sine, cosine, sine. And when I do that, the cosines reduce out of the little fractions. The sines reduce out of the little fractions. And so what I'm left with is, let's go ahead and multiply this out. Might not need to do this step, but let's go ahead and do it anyways. We've got cosine theta sine squared theta minus cosine times cosine is cosine squared times the sine over what's left is sine minus cosine. Sine minus cosine. Now, I want you to avoid the temptation, because I know you're tempted, to just cross off cosine, because I see cosine on top and bottom, or to cross off sine, because I see sine on top and bottom. We can only reduce if the fraction is factored first. You need to factor. That's why we spend so much time factoring in Algebra 1 and Algebra 2, because factoring is so essential in order to solve the problem, to simplify expressions. So I need to look at this numerator. What is the common factor I see? Well, they both have a sine and a cosine. So let's factor out sine, cosine. When I factor that out, the cosine's gone, one sine is gone, there's one sine left. Cosine's gone, but there's one cosine left. And the sine is gone. All over sine minus cosine. Now that it's factored, now you can reduce entire factors. So the sine minus cosine appearing in numerator and denominator can reduce out. And that just leaves me with sine cosine. Which is what we wanted. Sine cosine completes my proof. QED. Drop my pen. 1 second. And we're back with the pen. Excellent. So hopefully that helps you with that proof. Practicing with proofs. Great question came in from TikTok from I'm Reading Too. I just started trig today. What do I suggest? Really great tip to suggest for trigonometry is, first off, it's important you get lots of practice. Don't skip on the practice and avoid the temptation to practice what you're familiar and comfortable with that you like, but practice the hard stuff because that's how you're going to get better. If you don't do the hard stuff, you're never going to get better. The second thing I recommend is really pay attention to how the things work together instead of trying to memorize a whole bunch of formulas, because you're going to feel like you're memorizing a lot of unrelated things. For example, one of the problems that we do is we say, actually, let's back way up. Let's look at how this is all connected to the unit circle. Never can draw enough unit circles in a trig review session. In the unit circle, we'll look at angles formed in the unit circle, making these little triangles inside the circle. And you can see as the tip of this triangle moves around the circle, that triangle is going to change shape. But what's important about this circle is the radius is always equal to 1. The other thing that you need to know is that the x coordinate, the x distance, has another name in trigonometry. We don't say x. What we do is we say cosine. And the y distance, the vertical distance, we won't say y, we won't say vertical distance, we're going to call it the sine. But what's nice is from geometry, we know that a triangle has an important relationship, that a squared plus b squared equals c squared. So I can take this side squared, is going to be sine squared, plus that side squared, which is cosine squared, equals the hypotenuse squared, which is 1. This is probably the most important, most used, most needed trig identity that comes up all the time. Sine squared plus cosine squared equals 1. But what's nice is this one kind of lends to 2 more trig identities that are Pythagorean identities, but you don't have to memorize them if you know where they come from and how they work. If I were to go through and divide each of these by sine squared, all the way across, we'll divide by sine squared. It's going to give me another Pythagorean identity because sine squared divided by sine squared is 1. Cosine squared divided by sine squared, cosine divided by sine, we know is cotangent squared. 1 divided by sine squared, the reciprocal of sine squared has been defined as cosecant squared. And so by going through and dividing them by sine, we came up with our second Pythagorean identity. So you don't actually have to memorize this Pythagorean identity if you know how to get it from that all-important sine squared plus cosine squared equals 1. But we don't have to just divide by sine squared. We could have divided by cosine squared instead. And if I go through and divide by cosine squared all the way across, you get a third Pythagorean identity. Sine squared divided by cosine squared, we know is tangent squared. Cosine squared divided by cosine squared, anything divided by itself, is 1. And the reciprocal of cosine, that's secant. So what we just did is, because we kind of know the relationship on the unit circle, has a hypotenuse of 1, its x-coordinate is cosine, its y-coordinate is sine. That leads to the Pythagorean identity from a squared plus b squared equals c squared, which leads to the cotangent and the tangent Pythagorean identities as well. Excellent. Good point came up about, isn't it vertical horizontal displacement and not distance? That is a really good point, because if the x-coordinate is negative, the displacement or the movement from 0 is going to be a negative value. So that's how we get negative values from cosine and negative values from sine. If we go left and down, those are negative backwards values. So you are correct. It's not really a distance because distance has to be positive. So we're going to say displacement might have been a better word to use. Just use this all the time, and now you know why it's 1. Excellent. Yeah, exactly right. It's the unit circle. The radius of the unit circle is 1. That's a really important concept. Helps it kind of also makes sense why we're doing this. Trigonometry of all of the math should be the easiest one to say, why does this work? Always ask your teacher, why does this work? Make sure you understand why it works, because if you understand why it works and where it comes from, it makes more sense how we're getting each of these results. All right, I got another request for a solving trig equations. Wants to do it with the Pythagorean identity, not Pythagorean, with the quadratic formula. Make sure I'm reading correctly. Yeah, quadratic formula. Okay. These we can kind of make up a little bit more lazy. Let's go 3 cosine squared of theta plus 2 cosine of theta minus 1 equals 0. And that actually factors. So let's make it minus 4 so it doesn't factor. 12, 6, 2, 4, 3. Yeah, okay, that one doesn't factor. You wanted one with the quadratic formula. So we're going to end this session with a bang. Remember, we are here every week. If you want to know the schedule, scan this QR code so you don't miss our future lives. We're here every week answering your questions. This hour is specifically about trig. We're going to wrap up with this question where we're going to use the Pythagorean theorem. Or, whoa, I did Pythagoras again. That was the last example. We're doing the quadratic formula where A is B, A is the 3, B is the 2, and C is the 4. So the quadratic formula is that x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. That's a good one to have memorized. There's a lot of great songs on TikTok, on Instagram, on YouTube to help you memorize it. Let's just plug in our values and see what we get. X, actually it's not x, it's what this is. So it's the cosine. Cosine is equal to that. So the cosine of our angle is equal to the opposite of b, which is -2, plus or minus the square root of b squared. 2 squared is 4, minus 4 times a, which is 3, times c, which is -4, all over 2 times a, which is 3. And then it's just a matter of simplifying this. Let's see what we get for the cosine of theta is equal to -2 plus or minus 4 times 4 is 16. 16 times 3 is 48. 48 plus 4 is 52. All over 6. And I'm probably going to need to use a calculator to get kind of an estimate at the square root of 52 here. Square root of 52 is about 7.2. So cosine is equal to, we're going to do both the plus and the minus, -2 plus 7.2 divided by 6, and -2 minus 7.2 divided by 6. Going back to my calculator. -2 minus 7.2 divided by 6. This one's -1.533. -2 plus 7.2 divided by 6. That is 0.8667. Now remember, cosine values oscillate between -1 and 1. It is the x coordinate on the unit circle. The biggest x coordinate you can get is +1 or -1. This last one is outside of that domain, so we're going to dump it out. And so we just need to figure out when does cosine equal 0.8662. So I'm going to come up here. We're going to do the cosine inverse on my calculator of 0.8667. Sorry, I can't read my own handwriting. And let's go ahead and do this in degrees because we're doing ugly decimals anyways. Cosine inverse of 0.8667. That's going to be basically just shy of a 30-degree angle, 29.9 degrees. So if our angle theta is 29.9 degrees, this equation ends up being equal to 0, doing it by using the quadratic formula, because cosine squared and cosine just act like our x's. Algebra works the same way from that. All right. Well, thank you so much for joining us. We are unfortunately out of time. It goes so fast. So I want to start by giving a huge thank you to all of you for joining us. Your engagement, your questions have been great. It has been such a pleasure to share my joy of trigonometry, mathematics with you today. Hopefully I made it a little more enjoyable for you as well. Before you go, make sure you're at chegg.com. we're here to support you all semester long, 24/7, to help you with your toughest subjects with lives. Scan the QR code, or also you can follow us on TikTok, YouTube, Instagram, Twitch, and more for great learning content like this. Remember, we're here every week at this time, so make sure you're following. Make sure you follow me at Wallace STEM, and until the next time I see you,